Years of probabilistic combinatorics as well, and it is very, very interesting. But before proving that, I just want to show you what we can do if you want to just localize it, and by localizing, I mean your transition probability PSU and V is that if you are in that local stuff, for example S, for example you have a big data vault, G is equal V and E. So G is equal to V and E, and from this we want to concentrate on just a subset of these vertices. And your transition probability now becomes like this. For just a local version of that, we say that if you're out of this set S, then it is same as usual, PU and V. But if you're out of this set, such as this set, these vertices, then your transition probability is 0. So P is just D localized on S, AS. And it's just ds half I minus Laplacian S ds half. And this satisfies the Dirichlet boundary condition, but for the set S. If you remember, there was a set, and it had a boundary. So if you just extend the theorem to the localized version, which is S of V and U, of course P here is just a lazy random walk, and so it's just I plus P over 2 because it's a lazy random walk. So it is upper bounded by 1 minus beta squared TVS divided by 8 to the T times degree of U divided by degree of V, and the same definition for beta, but this time T is just a subset of beta, T and V and S, infimum of T. T is just a subset of that S over volume of T. And so the interesting proof, you should use some facts. For example, one interesting fact is that you can write for a function f from V to R. The fact is f times D, the degree matrix, times P. So this is just if you evaluate for vertex V, it's just a number, and the inner product is the number, so it's a scalar, and this is a scalar, and then divided by 2, so it becomes scalar. And G1 of V is upper bounded by dV. So the fact you can find the complete proof in the article of 2007 article of Fan Chung, but the interesting things that I want to recall is just saying that first of all she has written it as such a beautiful things in order to make it cleaner, because the original proof could be very messy, but this proof is very clean and short as well, because it just uses some facts. For example, this is fact number 1, and using just fact number 1, fact number 2, fact number 3, you can prove that theorem. Because because, for example, by saying that f of k of v is just by defining different functions. For example, one of the typical functions that people use is this, u and v divided by d of v. And the interesting things about this function is that if you just multiply fk by ds ps and evaluate it for vertex v, then it becomes recursive stuff. It becomes recursive. That is interesting for us because everything is just getting simplified and like geometric stuff. fk plus 1 d of v. So the proof becomes very easier, and sometimes instead of this function, in order to order the function, we use another function which is like this. For example, you could use this function. pk, p is the, again, lazy transition probability, lazy random walk, u of v minus p of v divided by p of v. So instead of this function, if you use this function, you can prove it again. So for different functions, you have different results. And this is the art of Fan Chung in 2007. And the name of her article is Random Walks and Local Cuts in Graphs. The reason that I selected this article among many different articles is just, first of all, I have read many different proofs of lovasz and Siminovitz. All of them are too long. All of them use several different functions. But what Fan Chung has done is quite peculiar and interesting because she has used the minimum amount of lines for the proof of that in order to show us indirectly that the proof should be simple because all of the Markov chains and all of the theorems are very simple. So the proof should be very simple. And using some interesting and basic facts, we can prove those results of Siminovitz. And also in this paper, she has used it for the local version as well. And this proof is interesting for theoretical purposes as well, because you see how to prove a theorem in a different way. So Lapchi law, so there are many people. First of all, lovasz and Siminovitz in 1990 and 1993. Here you see a proof. Here you see an improved thing, but it is more focused on the finding the volume of a convex body. But this article was very interesting, good proof. Then there are several peoples, such as Lapchi Lau in Waterloo, I guess. He has understood it very well, and he has proved it in several different ways with his PhD student. But his proofs are very long. And you see many others have proved this theorem of lovasz and Siminovitz, but the proof of Fan Chung in 2007 in Journal of Linear Algebra and Application is very beautiful for me. I mean, personally, I like this proof for many reasons. First, it is short. It's very short. Just using fact 1 and fact 2, you can prove many great results. Second, she has generalized it for local versions. So as I showed you, she has used local Chiger inequality. And so instead of the general Laplacian over V times V, we are working with Laplacian over S times S. And third, then you can see that how different mathematicians having different proofs, and each proof allows us to learn new basic facts about these Markov chains. I mean reversible Markov chains, random walk on the graph. And so in the next weekend, I will be talking about, I will create, first of all, a new playlist called Random Walk on Graph. And then I try to just simplify major results, major ideas in Markov chains, and particularly reversible Markov chains. But I mean, the ideas of Yuval Perez, which I really like, the ideas of Aldous, David Aldous, a great mathematician. He has also written 2 books. And so I try to combine different ideas. For example, here I will talk about heating times, how cover time, how heating times, effective resistance of electrical networks. All of these ideas are related to each other. How it is related to, for example, tau of relative, and I mean 1 over 1 minus lambda 2, and how all of these things, so heating times, cover time, exit time, recurrent time, eigenvalues, all of these things, how they are related to each other, and how we can actually create better algorithm for sparse graphs. For example, multi-cut. For example, many sparse cuts. Many of these beautiful applications, we can do it with just understanding basic things like heating times, their relationship between their formulas, which is just expectations, and then some values such as pj. So very basic things, basic variables that we all know, how it is related to heating times and cover times. So the work of Aldous is very important. David Aldous. The work of Yuval Perez is very important. And many other people, such as James Lee, Shayan Owais Qaran, and many authors. For example, I forgot his name, Nathan Lee, I think. But, for example, he has 2 books on Markov chain. One of them is Reversible Markov chain. Yuval Perez has three books. One of them is about networks. I mean, some examples of trees and networks. The other one about Markov chains and mixing time. The other recent book is about fractals, because he's interested in Hausdorff dimension, fractal dimensions, and those things as well. So if we combine all of these books, we can almost understand the major concepts and major ideas for Markov chains to be able to use it for future algorithm in computer science. For example, in computer science, there are some problems such as k-cut, such as if you want many sparse cuts, min cut, ST cut, multi-cut, Steiner cut, all of those problems in computer science can be well understood by some concepts such as heating time, cover time, effective resistance that, as you know, Spielman has talked about it, effective resistance. By the way, Spielman has used the idea of lovasz and Siminovitz that I just described, Siminovitz, and he's inspired by that, I guess, because he has reference to that. And so all of these concepts, beautiful concepts such as cover time, heating time, effective resistance, what else? Recurrence time, what else? So all of them can be applied in order to create better algorithm, in order to understand what is conductance, what is local conductance, what is many different concepts that are not as popular as these concepts, but they are very important for progress of spectral graph theory and the beautiful problems that we love, such as k-cut, sparse cut, Steiner cut, online Steiner cut, stochastic Steiner cut, and many of those things. All right, so have a great weekend. Cheers.